Picture this. You wake up one morning and start wondering where everything came from. Not just your coffee or your house, but literally everything. Every star, every galaxy, every atom in your body. Where did it all begin? This is the question that keeps cosmologists awake at night. And the answer might surprise you. For decades, we've been told the universe started with the Big Bang, a massive explosion that created space and time itself about 13.8 billion years ago. It's the story we learned in school, the explanation that seems to make sense. But what if that's not the whole picture? What if the universe didn't actually begin at all? What if instead, it's been oscillating back and forth through cycles for eternity, like a cosmic yo-yo that never stops? This is the heart of one of the biggest debates in modern physics. On one side, we have the Big Bang theory, backed by mountains of evidence and decades of observations. It tells us the universe exploded into existence from an incredibly small, incredibly dense point called a singularity. On the other side, we have the Big Bounce theory, which suggests the universe contracts and expands repeatedly, with no true beginning or end. Each contraction phase ends in what would have been a big crunch, but instead of crushing everything into oblivion, the universe rebounds and starts fresh. Both theories try to answer the same fundamental question, but they lead to wildly different conclusions about reality itself. If the Big Bang is correct, then time had a beginning. And asking what came before is like asking what's north of the North Pole. The question doesn't even make sense. But if the Big Bounce is right, then the universe is perpetual, transforming through death and rebirth forever. Your atoms might have existed in a previous universe, in forms we can't even imagine. Think about what this really means for a moment. The Big Bang says that 13.8 billion years ago, there was no space, no time, no matter, no energy, nothing at all. Then, suddenly, everything burst into existence in a fraction of a second. Space itself began expanding at incredible speeds, carrying matter and energy with it. Within the first second, the fundamental forces of nature emerged. Within 3 minutes, the first atomic nuclei formed. After 380,000 years, atoms assembled and light could finally travel freely through space. Stars lit up hundreds of millions of years later. Then galaxies formed, planets emerged, and eventually, on at least one rocky world orbiting an ordinary star, life appeared and evolved intelligence. That's an incredible story. It's a narrative with a clear beginning, a middle we're living through, and potentially an end billions or trillions of years in the future. It's a story humans can wrap their minds around because it has the structure we expect from stories. Beginning, middle, end, creation, evolution, conclusion. The Big Bounce offers something radically different. Imagine the universe as a cosmic accordion, squeezing together and then expanding out over and over again without end. Each compression doesn't destroy the universe, but squeezes it to incredibly small sizes before quantum effects take over and force everything back outward. The expansion we observe now is just one phase in an endless process. Before our current expansion, there was a contraction. Before that contraction, an earlier expansion. And so on, stretching backward through time without limit. In this view, there's no creation moment. The universe has always existed in some form. What we call the Big Bang is really just the most recent rebound, a transition point between the last contraction and our current expansion. Time doesn't have a starting point. Causality extends backward without end. Every cause has an earlier cause, chains of events linking together without a first link. This isn't just an academic debate between scientists with too much free time. The answer shapes how we understand existence itself. It affects our concepts of time, causality, and whether the universe had a creator or has simply always existed in some form. Philosophers have wrestled with these questions for thousands of years. But now we have telescopes, mathematics, and experiments that might actually give us answers. Consider the implications for consciousness and meaning. If the universe had a definite beginning, then everything that exists, including human consciousness, emerged from that initial moment. We're part of an unfolding story that started at a specific point. There's a directionality to cosmic history. But if the universe is timeless, oscillating through boundless transformations, then our existence is just one temporary arrangement of matter and energy in an endless process. We're just one chapter in an unlimited book. Here's the thing though, both theories have problems. The Big Bang leads us to a singularity, a point where all the laws of physics break down and nothing makes sense anymore. It's like the universe's way of saying, I don't want to talk about it. At this singularity, density becomes incomprehensibly high. Temperature reaches unimaginable extremes, and our equations give nonsensical results. General relativity, Einstein's beautiful theory that describes gravity and space-time, simply stops working. It's like hitting an error message in the universe's operating system. Meanwhile, the Big Bounce has to explain how a universe can collapse without being destroyed, and how it can rebound without leaving obvious traces we should have already detected. When matter compresses to unimaginable densities, quantum mechanics and general relativity both become important, and we don't have a complete theory merging these two frameworks. Loop quantum gravity and string theory offer possibilities, but they're not fully developed or experimentally confirmed. Throughout this documentary, we're going to explore both sides of this cosmic debate. We'll trace the history of how scientists developed these ideas, starting from Einstein's general relativity and extending through decades of observations and theoretical developments. We'll examine the evidence supporting each theory and look at the problems that keep researchers up at night. We'll talk about recent discoveries from the James Webb Space Telescope that launched in 2021, and we'll meet the scientists championing each view. We'll also explore the philosophical dimensions that we'll examine in depth later. What would a beginning or endless existence mean for reality? How do these scientific theories relate to different worldviews? These questions will guide our journey through cosmic origins. By the end, you might not have a definitive answer. Science rarely works that way, especially for questions this profound. But you'll understand the questions better, appreciate the evidence and arguments on both sides, and recognize what's at stake. You'll see how science tackles the biggest possible questions through observation, mathematics, and logical reasoning. Whether it started with a bang or has been rebounding forever, the fact that we're here to ask these questions is perhaps the most remarkable thing of all. We're made of atoms forged in stellar furnaces, assembled on a rocky planet, evolved through billions of years of natural selection, now capable of contemplating the universe's origins and nature. So let's start at the beginning. Or should I say, let's start at what might be the beginning. Because as you're about to learn, even that simple phrase is more complicated than it sounds. To understand how we got to this debate, we need to go back to the early 20th century, when physics was experiencing its own revolution of ideas. The story starts in 1915, with a German physicist named Albert Einstein. You've probably heard of him. Einstein had just finished his general theory of relativity, a revolutionary way of understanding gravity, not as a force, but as the bending of space and time itself. Think of space-time like a trampoline. Put a bowling ball on it, and the fabric bends. Roll a marble nearby, and it curves toward the bowling ball. Not because the bowling ball is pulling it, but because the fabric itself is warped. That's essentially how Einstein explained gravity. Massive objects curve space-time, and other objects follow those curves. Planets orbit the sun not because they're being pulled by an invisible force, but because the sun's mass creates a depression in space-time that planets naturally follow, like marbles rolling around the inside of a bowl. But Einstein's equations had a strange implication that bothered him. They suggested the universe couldn't be static. It had to be either expanding or contracting. This troubled Einstein deeply because everyone in 1915 assumed the universe was perpetual and unchanging. The cosmos was supposed to be a stage where events played out, not an actor itself. Einstein found this idea of a dynamic universe so uncomfortable that he added a mathematical fudge factor called the cosmological constant to keep the universe still. It was like adding training wheels to his elegant theory, because the result seemed too wild to believe. Einstein wasn't alone in assuming a static universe. This belief went back thousands of years. Ancient Greek philosophers imagined the heavens as perfect and unchanging, contrasting with the messy, chaotic Earth. Medieval cosmology placed Earth at the center of concentric celestial spheres that rotated without end. Even after Copernicus displaced Earth from the center and Newton explained planetary motion through gravity, the cosmos itself seemed timeless and unchanging. Then in 1922, a Russian mathematician named Alexander Friedmann took Einstein's equations seriously without the cosmological constant fudge factor. Friedmann was an interesting character. He worked as a pilot in World War I, survived the Russian Revolution, and pursued mathematics despite the chaos surrounding him. He worked out several solutions, showing the universe could expand, contract, or oscillate. Friedmann didn't have much observational evidence, just mathematics, but his work laid the groundwork for everything that followed. Friedmann's solutions described three basic possibilities. In an open universe with negative curvature, like a saddle shape, expansion would continue forever and accelerate. In a closed universe with positive curvature, like a sphere, expansion would eventually stop and reverse into contraction. In a flat universe with zero curvature, expansion would continue forever but gradually slow down, approaching but never quite reaching a halt. These mathematical possibilities seemed abstract and disconnected from observations. Sadly, Friedmann died young in 1925 from typhoid fever, never seeing his ideas vindicated. He was only 37 years old. The next major player was Georges Lemaitre, a Belgian priest and physicist. Lemaitre was a fascinating figure, someone who navigated both science and faith without seeing them as contradictory. He studied physics and mathematics, served in World War I, then entered seminary while continuing his scientific education. In 1927, Lemaitre independently derived similar solutions to Friedmann's and went further, proposing something radical. He suggested the universe started from what he called a primeval atom, or cosmic egg, a single point containing all matter and energy. From this cosmic egg, the universe hatched and began expanding. Lemaitre called this the hypothesis of the primeval atom. It was a bold idea, suggesting a definite beginning to the universe at a finite time in the past. When Einstein first heard this idea, his reaction was dismissive. He reportedly said to Lemaitre, "Your calculations are correct, but your physics is atrocious." Einstein still clung to his vision of a static universe, and the idea of a definite beginning seemed philosophically troubling, but observational evidence was about to force everyone's hand. In the 1920s, telescopes were getting bigger and better. The Mount Wilson Observatory in California housed the Hooker telescope, at that time the world's largest, with a mirror 100 inches across. Astronomers were using these powerful instruments to study fuzzy patches of light called nebulae. An astronomer named Vesto Slipher, working at Lowell Observatory in Arizona, made curious observations. When he looked at the light from these spiral nebulae, he found it was shifted toward the red end of the spectrum. This redshift suggested the objects were moving away from us. By 1925, Slipher had measured redshifts for dozens of these nebulae, and most showed motion away from our galaxy. Then came Edwin Hubble, working at the Mount Wilson Observatory. Hubble was a complex character, sometimes arrogant, always ambitious, trained as a lawyer, but drawn to astronomy. In the early 1920s, he used the Hooker telescope to resolve individual stars in some nebulae, proving they were distant galaxies beyond the Milky Way. This discovery itself was revolutionary, expanding the known universe from one galaxy to potentially billions. In 1929, Hubble made his most crucial discovery. He measured distances to various galaxies using a class of variable stars called Cepheids. Cepheid variables pulsate regularly, brightening and dimming over days or weeks. Henrietta Leavitt had discovered in 1912 that a Cepheid's pulsation period relates directly to its intrinsic brightness. Measure the period, know the true brightness. Compare to observed brightness, and you can calculate distance. This relationship gave astronomers a cosmic yardstick. Hubble measured Cepheid distances to several galaxies and compared them to their redshifts. What he found was stunning. The farther away a galaxy was, the faster it appeared to be moving away from us. The relationship was linear. Double the distance, double the recession velocity. This relationship is now called Hubble's law, though it should probably be Hubble-Lemaitre's law, since Lemaitre had predicted this relationship 2 years earlier. Picture dots painted on the surface of an inflating balloon. As you blow air into the balloon, every dot moves away from every other dot. No dot is special or central. The dots farther apart separate faster than dots close together because there's more rubber stretching between them. That's what Hubble found happening with galaxies. The universe itself was expanding, carrying galaxies along like boats on a rising tide. This observation changed everything. If the universe was expanding, then running the clock backward meant it must have been smaller in the past. Keep going back, and you reach a point where everything was compressed together. Lemaitre's primeval atom suddenly looked a lot more credible. Einstein visited Hubble in 1931 at Mount Wilson Observatory. After seeing the evidence firsthand, Einstein conceded his cosmological constant was his biggest blunder. The universe wasn't static after all, though interestingly, that constant would make a comeback decades later when scientists discovered the universe's expansion was accelerating. But the theory needed more development and predictions. In the late 1930s and 1940s, a colorful physicist named George Gamow picked up the torch. Gamow was a Russian émigré with a fantastic sense of humor. He escaped the Soviet Union in 1933 and brought a playful approach to serious physics. Gamow worked with his students Ralph Alpha and Robert Herman to figure out what the early universe would have been like if it started hot and dense. They calculated that when the universe was between 1 and 3 minutes old, it would have been hot enough for nuclear fusion to occur everywhere at once. Protons and neutrons could combine to form helium nuclei, along with traces of deuterium, lithium, and beryllium. Their calculations made precise predictions. About 75% of normal matter should be hydrogen, the simplest atom with one proton. About 25% should be helium with 2 protons and 2 neutrons. There should be tiny traces of deuterium, helium-3, and lithium-7. These ratios couldn't be explained by stellar nucleosynthesis alone. In 1948, Alpha and Herman made another crucial prediction. They calculated that if the universe started hot, there should still be leftover radiation from that early fireball. As the universe expanded, this radiation would cool. They estimated it should have cooled to about 5 degrees above absolute zero by the present day. This cosmic background radiation would fill all of space. It was a testable prediction, but technology in 1948 wasn't ready to detect such faint microwaves. The theory still needed a catchy name, though. That came from an unexpected source. Fred Hoyle was a British astronomer who hated the expanding universe idea. He was brilliant and combative, never shy about expressing strong opinions. Hoyle favored the steady-state theory, where the universe had always existed and new matter was continuously created to fill the gaps as space expanded. During a BBC radio broadcast in 1949, Hoyle discussed various cosmological theories. He mockingly referred to Lemaitre's idea as the Big Bang, trying to make it sound ridiculous and unscientific. The name was meant to be derogatory, but the name stuck, and even supporters of the theory adopted the term. Through the 1950s, the debate raged between Big Bang and steady-state proponents. Both sides made predictions and gathered evidence. Scientists designed observations to distinguish between theories. Radio astronomers counted distant radio sources, trying to see if their distribution changed over cosmic time. The stage was set for a decisive observation. In the next chapter, we'll explore the evidence that transformed this expansion of ideas into solid scientific theory and convince the community this wasn't just a mathematical curiosity. If you're going to claim the universe exploded into existence from a single point billions of years ago, you'd better have some solid evidence. Extraordinary claims need extraordinary proof, and the Big Bang theory has accumulated quite a bit of both over the decades. Let's walk through the major pieces of evidence that convince scientists this theory describes our actual universe. First, we have Hubble's law and cosmic expansion, which we touched on earlier. When Edwin Hubble measured galaxy velocities in 1929, he established something remarkable. Every galaxy we observe is moving away from us, and the relationship is precise. Double the distance to a galaxy, and its recession velocity doubles too. Currently, we measure this expansion rate at about 45 miles per second per megaparsec. That means a galaxy 1 megaparsec away, roughly 3.26 million light-years, recedes at 45 miles per second, while a galaxy 2 megaparsecs away recedes at 90 miles per second. This expansion isn't galaxies flying through space like shrapnel from an explosion. Space itself is stretching, carrying galaxies along with it. This distinction matters because it means the Big Bang didn't happen at a specific location. It happened everywhere, at once, and we can see evidence of it in every direction. When we measure the redshift of distant galaxies, we're seeing this expansion directly. Light waves stretch as space expands, shifting toward longer, redder wavelengths. The farther the galaxy, the more space has expanded during the light's journey, producing a greater redshift. This matches predictions perfectly and has been confirmed with thousands of galaxy measurements. Now, here's where things get really interesting. In 1965, two researchers at Bell Labs named Arno Penzias and Robert Wilson were testing a sensitive radio antenna. They kept detecting annoying background noise no matter where they pointed it. After ruling out interference from New York City, atmospheric effects, and even pigeon droppings on the antenna, they realized they'd found something cosmological. That noise was ancient light from when the universe was just 380,000 years old. At that time, the cosmos had cooled enough for electrons and protons to combine into hydrogen atoms. Before that moment, the universe was opaque, like being inside a cloud. Photons constantly scattered off free electrons, unable to travel far. But when atoms formed, the universe suddenly became transparent. Light could finally travel freely through space. The cosmic microwave background is that first light, stretched by expansion from visible wavelengths to microwaves over 13.8 billion years. It has a temperature of about 2.725 degrees above absolute zero, exactly what the Big Bang Theory predicted. This radiation fills the entire universe uniformly, coming from every direction. Penzias and Wilson won the Nobel Prize in 1978 for this discovery. Their accidental find provided the smoking gun evidence for the Big Bang. But the story doesn't end there. Scientists wanted to map this cosmic background radiation in detail to see if it was perfectly smooth or had variations. Between 1989 and 1993, NASA's Cosmic Background Explorer satellite, or COBE, mapped the microwave sky with unprecedented precision. It found tiny temperature variations, differences of only about 1 part in 100,000. These tiny ripples represented density fluctuations in the early universe, seeds that would eventually grow into galaxies and galaxy clusters. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001 and spent 9 years making even more detailed maps. Then the European Space Agency's Planck satellite, operating from 2009 to 2013, provided the highest resolution cosmic microwave background map we have. These missions revealed patterns matching Big Bang predictions with incredible accuracy. These temperature patterns are like cosmic barcodes, encoding information about the universe's composition, age, and geometry. From them, we've determined the universe is 13.8 billion years old, give or take about 20 million years. We've learned it's geometrically flat, meaning parallel lines stay parallel over cosmic distances. We've measured the ratio of ordinary matter to dark matter and dark energy. Another powerful piece of evidence comes from Big Bang nucleosynthesis, the formation of light elements in the universe's first few minutes. When the cosmos was between 1 and 3 minutes old, it was hot enough for nuclear fusion to occur everywhere at once. Protons and neutrons combined to form helium nuclei, along with traces of deuterium, lithium, and beryllium. The Big Bang Theory makes precise predictions about these element ratios based on the density and temperature of the early universe. Observations match these predictions remarkably well. About 75% of normal matter is hydrogen, 25% is helium, and there are tiny amounts of the other light elements. You can't get these ratios from stellar nucleosynthesis alone. Then we have the large-scale structure of the universe. When we map galaxy positions across billions of light-years, we see patterns. Galaxies cluster together along filaments and sheets, surrounding enormous voids with relatively few galaxies. This cosmic web structure arose from those tiny density variations we see in the cosmic microwave background. Computer simulations running Big Bang physics with cosmic microwave background initial conditions reproduce this structure beautifully. Start with the universe at 380,000 years old. Input the density variations from satellite data, let gravity work for 13.8 billion simulated years, and you get a universe that looks remarkably like ours. We can also observe how galaxy clustering has evolved over time by looking at galaxies at different distances. Remember, looking far away means looking back in time because light takes time to reach us. The patterns match predictions for how structure should have developed from Big Bang initial conditions. Even the universe's chemical evolution supports the theory. The first stars formed from pure hydrogen and helium created in the Big Bang. These stars fused heavier elements in their cores, then scattered them into space when they exploded as supernovae. Second-generation stars formed from gas, enriched with these heavier elements. This process repeated over billions of years, gradually increasing the universe's metallicity. When we observe very distant, very old galaxies, they show lower metallicity than nearby galaxies, exactly as expected. The most ancient stars we can find show compositions dominated by hydrogen and helium, consistent with formation from Big Bang material. The evidence supporting the Big Bang is diverse, coming from completely different types of observations that all point to the same conclusion. The universe expands. It has leftover heat from a hot beginning. Its light element ratios match predictions, and its structure grew from initial seeds. Each piece of evidence alone would be suggestive, but together they build an overwhelming case. For several decades, the Big Bang reigned supreme as the standard model of cosmology. But science isn't about declaring victory and going home. It's about pushing further, asking harder questions, and examining assumptions. And when scientists looked closely, they found some uncomfortable problems lurking beneath its success. The Big Bang theory works remarkably well for explaining what we observe. But it's not perfect. Like a car that runs great until you look under the hood and realize some parts don't quite fit together, the Big Bang has issues that keep theoretical physicists awake at night. These aren't minor quibbles. They're fundamental problems that suggest our understanding is incomplete. The biggest problem, literally and figuratively, is the singularity. Run the Big Bang backward, and you reach a point where all matter and energy in the universe was compressed into an incredibly small space with immeasurably high density and temperature. This is what mathematicians call a singularity, a place where equations blow up and give nonsensical answers. Here's the issue. Our physics theories, including general relativity, break down at a singularity. They can't describe what happens there. The laws of physics as we know them simply don't apply at those extreme conditions. To truly understand the Big Bang's starting point, we'd need a theory of quantum gravity that combines general relativity with quantum mechanics. We don't have that yet. Think about what a singularity really means. At this point, the entire observable universe, everything we can see extending 93 billion light-years in diameter, was compressed into a volume smaller than an atom. Density becomes boundless. Temperature reaches incomprehensible extremes. The curvature of space-time becomes unlimited. Every physical quantity that can have a value goes to extremes or undefined states. Physicists hate getting these kinds of results in their theories. When an equation gives such extreme answers, it usually means you're asking the wrong question or using the theory beyond its valid range. General relativity gives us singularities at the center of black holes and at the Big Bang. Most physicists believe these aren't real physical entities, just indications that general relativity breaks down at those extreme scales. Having your theory lead to a point where it stops working is philosophically and scientifically unsatisfying. It's like a novel that's brilliant for 999 pages and then just says, "And then something happened, but I can't tell you what," on the last page. Then we have what's called the horizon problem. The cosmic microwave background radiation has the same temperature in all directions to within 1 part in 100,000. That's incredibly uniform. Measure the temperature toward the north celestial pole, then toward the south celestial pole, regions separated by the entire sky. They're the same temperature to extraordinary precision. But here's the puzzle. Regions of space on opposite sides of the observable universe have never been in contact with each other, even at light speed. They're separated by more than 93 billion light-years today. Even accounting for expansion, these regions were never close enough in the early universe to exchange heat and reach thermal equilibrium. Light travels at 186,000 miles per second. Very fast by everyday standards, but finite. In the early universe, even traveling at light speed, there wasn't enough time for distant regions to communicate and equilibrate. Yet somehow they all ended up at the same temperature. Related to this is the flatness problem. The universe's geometry is remarkably flat. Curvature measurements from cosmic microwave background observations show the universe's spatial geometry is flat to within measurement error. The Planck satellite measured this flatness to incredible precision. The problem is that flatness is unstable in an expanding universe. A universe that starts even slightly curved will rapidly become more curved as it expands. For the universe to be as flat as we observe today, its initial conditions had to be fine-tuned to an absurd degree, something like 1 part in 10 to the 60th power. That's not impossible, but it seems incredibly unlikely without some physical mechanism forcing flatness. These problems led to the development of cosmic inflation theory in the early 1980s. Alan Guth, then a young physicist at MIT, proposed that the universe underwent a brief period of exponential expansion in its first fraction of a second. During inflation, space expanded by a factor of at least 10 to the 26th power, in about 10 to the negative 32 seconds. Inflation elegantly solves both the horizon and flatness problems. The entire observable universe came from a tiny patch of space that was in thermal equilibrium before inflation. Regions now separated by vast distances were once so close together they could exchange heat. Then inflation blew up this tiny region to cosmic scales. Inflation also drives the universe toward flatness naturally. Take any curved surface, expand it by 10 to the 26th power, and locally, it will appear flat. After inflation ended, the universe continued expanding at a more sedate pace, following the standard Big Bang model. While inflation is widely accepted, it's not without problems. We don't know what caused inflation or what the inflaton field was that drove it. The inflaton is a hypothetical scalar field that permeated space and drove exponential expansion. But what is this field fundamentally? Why did it exist? Why did it turn on and why did it turn off? There are dozens of different inflation models, and we can't yet distinguish between them observationally. By adjusting parameters, inflation can be made to fit almost any observation, which makes some scientists nervous. Some critics, like Paul Steinhardt, who helped develop early inflation models, now argue that inflation creates more problems than it solves. Perpetual inflation potentially generates a multiverse of pocket universes with different physical laws. Some physicists find this exciting, others find it disturbing, arguing it makes the theory unfalsifiable. Then we have the question that everyone asks eventually. What happened before the Big Bang? If the Big Bang created space and time, then asking what came before is meaningless. Time itself didn't exist beforehand, so there was no before. It's like asking what's north of the North Pole, but that answer rarely satisfies people. Our brains are wired to think in terms of cause and effect, and an effect without a cause feels wrong. So, a universe that begins existing without a prior cause seems to violate basic logic. Yet if time itself began with the Big Bang, there's no prior time in which a cause could occur. Some physicists speculate about quantum fluctuations, creating the universe from nothing, though defining nothing gets tricky. Others propose the Big Bang emerged from a previous state. These ideas push the question back, rather than answering it. More recently, observations from the James Webb Space Telescope have added new wrinkles. Since launching in 2021 and becoming operational in 2022, JWST has been peering deeper into the universe's past than ever before. We're seeing galaxies that appear surprisingly mature and massive when the universe was only a few 100 million years old. According to standard Big Bang cosmology with inflation, early galaxies should have been small, irregular, and still forming. Instead, JWST is revealing galaxies that look more organized and massive than models predicted. Some appear to contain more stars than should have been possible to form in the available time. This doesn't necessarily mean the Big Bang is wrong, but it suggests our understanding of galaxy formation might need revising. Perhaps stars formed more efficiently in the early universe than we thought. Maybe dark matter played a different role than models assume. Most cosmologists think these observations will be explained within the standard framework once we better understand early astrophysics. There's also the ongoing mystery of dark matter and dark energy. Observations indicate normal matter makes up only about 5% of the universe's total mass energy content. About 27% is dark matter, detected only through gravitational effects. The remaining 68% is dark energy, a mysterious component causing the universe's expansion to accelerate. The Big Bang theory itself doesn't predict or explain dark matter and dark energy. They're added to the model based on observations, but we don't know what they fundamentally. These mysteries highlight how much we don't understand. All these issues create openings for alternative theories. They suggest that while the Big Bang captures important truths about cosmic history, it might not be the complete story. Maybe there's a way to avoid the singularity entirely and explain cosmic origins without requiring such extreme initial conditions. This brings us to the Big Bounce theory. Imagine the universe as a cosmic heartbeat, expanding and contracting in a perpetual rhythm. This is the essence of the Big Bounce theory. Instead of the universe beginning in a singularity and expanding forever, the rebound proposes something more elegant. The universe contracts, yes, but instead of collapsing into a singularity, it rebounds. The crunch becomes a bounce, and a new phase of expansion begins. This process could have been happening forever, with no true beginning or end. The idea of oscillating cosmology isn't new. Ancient Hindu cosmology described cycles of creation and destruction over vast timescales. In Western science, German philosopher Friedrich Nietzsche wrote about recurrence without end in the 19th century, though without scientific basis. But modern models are grounded in physics and mathematics. The first scientific exploration came from Richard Tolman in the 1930s. Tolman worked with Einstein's general relativity equations and explored whether a universe could contract after expanding. He developed models where the universe oscillated, rebounding between expansion and contraction phases. Each phase would be longer than the previous one because entropy increased each time. Tolman's models had a problem though. Extrapolating backward, the phases got shorter and shorter, eventually reaching a first phase that started from a singularity. So even Tolman's oscillating universe had a beginning. The model also struggled with entropy, which always increases according to thermodynamics. For decades, these models languished while the Big Bang took center stage. But in the late 1990s and early 2000s, new physics opened fresh possibilities. The key breakthrough came from loop quantum gravity, an attempt to quantize general relativity and understand what happens at the smallest possible scales. In loop quantum gravity, space itself is quantized, made of discrete chunks rather than being indefinitely divisible. Think of space like a fabric woven from threads rather than a smooth sheet. At extremely small scales, about 10 to the negative 35 meters, space has structure. This is called the Planck scale, where quantum effects of gravity become important. Martin Bojewald and Abhay Ashtekar at Pennsylvania State University applied loop quantum gravity to the early universe. They found something remarkable. When matter is compressed to enormous densities, quantum gravity effects create a repulsive force. This quantum rebound prevents the universe from collapsing into a singularity. Instead, the collapsing universe reaches a minimum size, then rebounds into expansion. This resolves the singularity problem we discussed in Chapter 4. There's no point where physics breaks down. The equations remain valid throughout the transition, describing a continuous evolution from contraction through rebound to expansion. The universe's history extends backward beyond the rebound into a previous phase. Another influential model comes from Roger Penrose, the British mathematician and physicist who won the Nobel Prize in 2020 for his work on black holes. Penrose proposed conformal cyclic cosmology in the early 2000s. His model is different from loop quantum cosmology but shares the oscillating concept. Penrose starts by considering what happens in the very far future of an accelerating universe. Eventually, all matter decays or falls into black holes. Those black holes eventually evaporate through Hawking radiation. After an unimaginably long time, the universe contains only radiation and empty space expanding forever. Here's Penrose's clever twist. In such a universe, there are no clocks and no rulers. Without matter, you can't measure distance or time in the usual way. Penrose argues that this far future state is mathematically equivalent to the Big Bang's initial state. The end of one cosmic aeon seamlessly becomes the beginning of the next through a mathematical transformation. Conformal cyclic cosmology makes testable predictions. Violent events in the previous aeon, like colliding supermassive black holes, should leave imprints on the cosmic microwave background as circular patterns. Penrose claims to have found such patterns and calls them Hawking points. However, most cosmologists remain skeptical, arguing the patterns could be statistical coincidences. String theory offers additional scenarios. Paul Steinhardt and Neil Turok developed the ekpyrotic universe model in the early 2000s. This uses ideas from M theory, involving higher dimensional brains. In their model, our universe is a three-dimensional brain in higher dimensional space. Periodically, it collides with another parallel brain. These collisions release enormous energy, appearing to us as a Big Bang. The ekpyrotic model explains cosmic uniformity differently than inflation. Before the collision, the brains were smooth and flat. The collision transferred this uniformity to matter and energy in our universe, producing the cosmic microwave background's remarkable sameness without requiring rapid inflation. What all these models share is the rejection of a true beginning. The universe transforms and changes, but it doesn't come into existence from nothing. There's always something before, whether a previous phase, a contracting period, or a higher dimensional structure underlying apparent beginnings. This has profound philosophical implications that we'll explore more deeply in Chapter 7. If the universe is timeless, then questions about ultimate origins dissolve. You don't need to invoke quantum fluctuations from nothing or speculate about multiverse generators. On the other hand, these models raise their own questions. If the universe rebounds forever, was there a first rebound? If there's no first instance, and the transformations extend back without limit, how do we make sense of that? Our brains struggle with boundless regression. There's also the entropy problem. Each transformation should increase disorder. After limitlessly many transformations, shouldn't the universe be in a maximum entropy state where nothing interesting happens? Some models try to solve this by having entropy reset during the rebound, though the mechanism remains unclear. Despite these philosophical puzzles, these models offer concrete physics that might be testable. Loop quantum cosmology makes predictions about very early universe conditions. The ekpyrotic model predicts different cosmic microwave background polarization patterns than inflation. Penrose's model predicts specific circular patterns. These predictions provide ways to potentially distinguish between frameworks. The key insight is that singularities might not be fundamental features of reality. They might be artifacts of using general relativity beyond its valid range. Just as special relativity resolved issues with Newtonian physics at high speeds, quantum gravity might resolve singularities, replacing them with rebounding transitions. Whether any specific model is correct remains an open question. They're all speculative, extrapolating physics into regimes we can't directly test. But they represent serious scientific alternatives, grounded in mathematics and potentially testable through observations. In the next chapter, we'll examine what evidence and arguments support these alternatives and how they stack up against the Big Bang's observational successes. The Big Bounce might sound like pure speculation, but it's grounded in serious theoretical physics and makes testable predictions. While it doesn't have the overwhelming observational support the Big Bang has accumulated, these models offer compelling advantages and some intriguing observational hints. The strongest argument for these models is theoretical elegance. They solve several Big Bang problems naturally without requiring additional assumptions. Take the horizon problem we discussed in Chapter 4. In a rebounding universe with a pre-rebound contraction phase, widely separated regions were once close together during the contraction. They had plenty of time to reach thermal equilibrium before rebounding into the expansion we observe. No inflation needed. Similarly, the flatness problem evaporates. In these models, the universe naturally tends toward flatness during expansion phases. Any initial curvature gets stretched out over multiple transformations. The rebound mechanism itself can also enforce flatness as a condition for a smooth transition. Perhaps most importantly, as we covered in Chapter 4, these models eliminate the singularity. The universe never reaches the extreme densities where physics breaks down. The rebound happens at finite, though extremely high, density where quantum gravity effects become strong enough to prevent further collapse. Loop quantum cosmology provides mathematical detail for this mechanism. The calculations show that as matter compresses, quantum geometry effects create an effective repulsive force proportional to density squared. This force becomes significant only at densities around 10 to the 94 grams per cubic centimeter, the Planck density. At these extreme densities, quantum corrections to Einstein's equations dominate. The universe stops contracting and rebounds with explosive force, similar to inflation but driven by quantum gravity rather than a scalar field. This quantum rebound launches the expansion phase we observe. Computer simulations of loop quantum cosmology demonstrate viability. Researchers can start with a contracting universe, follow it through the rebound using quantum-corrected equations, and see it emerge into an expanding phase matching our universe's properties. These simulations show that quantum effects naturally produce nearly scale-invariant density fluctuations, similar to what inflation generates. One key prediction distinguishes loop quantum cosmology from standard inflation. The power spectrum of density fluctuations should show subtle differences at large scales, corresponding to structures spanning billions of light-years. Specifically, loop quantum cosmology predicts slightly less power at the largest scales because the rebound introduces a minimum wavelength for fluctuations. Some researchers claim to see hints of this in cosmic microwave background data. The Planck satellite's measurements show less power at the largest angular scales than the simplest inflation models predict. This low quadrupole anomaly has been known since COBE in the 1990s. While most cosmologists consider it a statistical fluke, others suggest it might be evidence for a quantum rebound. Gravitational wave observations offer another testing ground. The rebound should have produced gravitational waves, ripples in spacetime from the violent quantum geometry fluctuations. These primordial gravitational waves would have characteristic frequencies and amplitudes depending on the rebound's details. Future gravitational wave observatories, like the space-based LISA mission planned for the 2030s, might detect these signals. Current gravitational wave detectors like LIGO and Virgo detect high-frequency waves from colliding black holes and neutron stars. But primordial gravitational waves from the early universe would have much lower frequencies, requiring space-based detectors with arms millions of miles long. LISA will search for gravitational waves in frequency ranges inaccessible from Earth, potentially revealing signs of exotic early universe physics. Building on what we learned in Chapter 3 about cosmic microwave background observations, this radiation also encodes gravitational wave information. Primordial gravitational waves leave distinctive patterns in the microwave background's polarization, specifically what's called B-mode polarization. Inflation predicts a certain level of B-mode signal depending on the energy scale. Loop quantum cosmology makes different predictions, typically lower B-mode amplitude. Several experiments are measuring cosmic microwave background polarization with increasing precision. Ground-based telescopes like the South Pole Telescope and the Atacama Cosmology Telescope scan the sky. The Simons Observatory, a new telescope array in Chile's Atacama Desert, began operations in 2024 specifically to measure B-modes. Regarding Penrose's conformal cyclic cosmology and its Hawking points predictions, as mentioned in Chapter 5, the broader cosmology community remains deeply skeptical. Multiple independent analyses failed to confirm the patterns, suggesting they might arise from statistical artifacts or overfitting data. This illustrates a challenge in testing these models. Many predictions involve subtle effects in data that already has random noise and systematic uncertainties. The James Webb Space Telescope discoveries we discussed in Chapter 4 present an interesting twist. Those surprisingly mature early galaxies that seemed hard to explain in standard Big Bang cosmology might be easier to accommodate if the universe rebounded from a previous phase. In a rebounding universe, structure formation could have begun during the contraction phase, giving galaxies a head start. This argument remains speculative and controversial. Most astronomers think JWST's findings will be explained within the standard cosmological framework once we better understand early star and galaxy formation. But it demonstrates how new observations can breathe life into alternative theories. Another consideration is philosophical rather than observational. Many physicists find timeless models more satisfying than a universe with a beginning. The idea that reality simply exists, transforming through phases but never starting from nothing, avoids uncomfortable questions about first causes and creation. This philosophical preference doesn't constitute evidence, but it motivates taking these models seriously and developing them rigorously. The ekpyrotic model's predictions about cosmic microwave background polarization haven't been clearly distinguished from inflation yet, but future experiments might change that. The model predicts a specific relationship between different types of density fluctuations, encoded in correlations between temperature and polarization patterns. One challenge for all these models is explaining entropy. If the universe has undergone limitlessly many transformations, each increasing entropy, why isn't entropy already at maximum? Some loop quantum cosmology models propose that quantum effects reset entropy during the rebound, though the mechanism remains unclear. Recent theoretical work has explored how quantum information might survive a rebound. Some models suggest that information gets encoded in the quantum state of the geometry itself during the rebound, then unpacked in the subsequent expansion. This remains highly speculative, at the cutting edge where quantum mechanics, gravity, and information theory intersect. The verdict on these models remains open. They address real problems in Big Bang theory and make testable predictions, even if confirming those predictions requires observations at the edge of current capabilities. They don't yet have smoking gun evidence like the cosmic microwave background discovery provided for the Big Bang. But they represent serious scientific alternatives, not just philosophical speculation. As observations improve, we'll gain better handles on distinguishing models. Measurements of cosmic microwave background polarization will continue with greater sensitivity. Gravitational wave astronomy will probe lower frequencies. Telescopes like JWST will map the early universe in unprecedented detail. Each new observation provides another chance to test predictions. We've explored the Big Bang and the Big Bounce separately. Now let's put them head to head, comparing how each theory handles the big questions and seeing where they agree, disagree, and leave mysteries unsolved. First, let's compare observational support. The Big Bang wins decisively here. It has decades of confirming evidence from multiple independent sources, as we detailed in Chapter 3. The cosmic expansion, the microwave background and its detailed patterns, nucleosynthesis explaining element abundances, and large-scale structure formation all support the framework. The Big Bounce, by contrast, doesn't contradict these observations, but also doesn't have unique evidence clearly favoring it. Most models are designed to reproduce the Big Bang's successful predictions while addressing its theoretical problems. They can explain the same data, but don't yet have their own definitive discovery. On theoretical elegance, the comparison flips. As we explored in Chapter 4, the Big Bang requires inflation to solve problems, but inflation itself raises questions about what drove it. The theory leads to a singularity where physics breaks down. It doesn't explain why the universe exists or what came before. The Big Bounce solves these problems naturally, as we saw in Chapters 5 and 6. No inflation needed because the pre-rebound contraction phase allowed thermal equilibrium. No singularity because quantum gravity effects create a rebound. No beginning from nothing paradox because the universe always existed in some form. These solutions feel more complete. However, these models introduce their own complications, like explaining entropy over boundless transformations. Different scientists weight these factors differently. Some prioritize observational confirmation above all, making the Big Bang the clear leader until alternative models produce unique predictions that observations confirm. Others value theoretical completeness and find the rebound more satisfying, despite weaker observational support. For explaining cosmic uniformity, the Big Bang with inflation invokes exponential expansion that stretched a tiny region across the observable universe. This works mathematically, but why did inflation happen? The bounce explains uniformity through the contraction phase, where distant regions were once close together. This seems more straightforward, but requires accepting a pre-rebound universe we can't directly observe. For geometry flatness, inflation drives the universe toward flat geometry automatically through exponential expansion. The rebound also naturally produces flatness through dynamics that either enforce it as a condition or stretch space during transformations. Both explanations work with no clear advantage. Regarding the singularity problem from Chapter 4, there's a stark difference. The Big Bang admits defeat, acknowledging physics breaks down, and we need quantum gravity to go further. The bounce claims to resolve this by replacing the singularity with a rebound, though the quantum gravity needed remains speculative. Regarding predictivity, both theories make testable predictions. The Big Bang predicted the cosmic microwave background decades before its discovery, a stunning success. Inflation predicted specific patterns in temperature fluctuations that have been confirmed. The bounce predicts subtle differences in large-scale power, specific gravitational wave signatures, and possibly circular patterns from previous phases. The philosophical dimension adds another layer, and this is where worldviews come into play most strongly. The Big Bang's definite beginning poses the question, why is there something rather than nothing? This question has occupied philosophers and theologians for millennia. Some see the Big Bang as compatible with religious creation stories, a scientific description of divine creation. Others argue it makes the universe explicable through natural laws without requiring a creator. The Big Bounce sidesteps these questions by having no beginning. The universe simply exists timelessly, transforming but never created. This removes the need for a first cause, but introduces the puzzle of boundless regression. Is an endless chain of causes more or less satisfying than a first uncaused cause? Different people answer differently based on philosophical intuitions. These connections to worldviews aren't just abstract. They reflect deep human questions about meaning and purpose. Whether the universe had a beginning or has existed perpetually affects how we conceptualize reality and our place in it. Let's hear from scientists in this debate. Carlo Rovelli, a leading quantum gravity theorist, strongly advocates loop quantum cosmology. He argues that removing singularities is crucial for physics to be complete, and that quantum effects at Planck scales must prevent extreme densities. Sean Carroll, a theoretical physicist and cosmologist, is more skeptical while remaining open-minded. He points out that perpetual inflation also produces a timeless multiverse in some sense, so the Big Bang framework needn't imply a true beginning to all reality. He emphasizes that we should follow observational evidence. Paul Steinhardt, who helped develop inflation theory but later became critical of it, has championed ekpyrotic models. He argues that inflation has become unfalsifiable because it predicts such a wide range of possible outcomes. Alternative models, he contends, make more specific predictions and are therefore more scientifically rigorous. Andre Linde, one of inflation's main architects, defends the theory vigorously. He acknowledges open questions but emphasizes inflation's successes in explaining observations and its natural emergence from many different high-energy physics scenarios. These debates play out at scientific conferences, in journal papers, and through public lectures. They're good-natured, scientists attacking each other's ideas rather than each other personally. This is how science progresses. Future observations will help resolve these debates. The Euclid Space Telescope, launched by the European Space Agency in 2023, is mapping the universe's large-scale structure with unprecedented detail. It's measuring how galaxy clustering evolved over billions of years, providing constraints on cosmic expansion history and dark energy properties. The James Webb Space Telescope will continue revealing the early universe, showing how the first galaxies and stars formed. These observations might favor models that better predict structure formation details. Gravitational wave astronomy is in its infancy. LIGO and Virgo have detected dozens of black hole and neutron star collisions since 2015. Future detectors will probe lower frequencies. The LISA mission, planned for launch in the 2030s, will search for gravitational waves from supermassive black hole mergers and potentially primordial sources. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will map the sky in infrared with wide fields, discovering thousands of supernovae and measuring cosmic expansion with high precision. Ground-based experiments continue measuring cosmic microwave background polarization. The Simons Observatory in Chile, the South Pole Observatory, and the planned CMB Stage 4 experiment will hunt for B-mode polarization signatures. Detecting primordial B-modes would constrain or rule out various models. All these missions represent opportunities for observations to guide theory. If alternative models' predictions are confirmed, support will shift. If they're ruled out, the Big Bang with inflation remains the standard. If observations continue matching both frameworks, then we'll need even more precise tests. One fascinating possibility is that neither model is quite right, and the truth involves elements of both, or something completely different we haven't imagined yet. Science has a history of finding that nature is stranger than our theories anticipated. These aren't just academic questions for specialists. They touch on profound issues about existence, time, causality, and our place in the cosmos. Whether the universe had a beginning or has existed, timelessly affects how we conceptualize reality. The debate will continue, sharpening as data improves. Scientists will propose new tests, refine theories, and hopefully narrow the possibilities. Eventually, observations might decisively favor one framework or point towards something new. Until then, we appreciate both the Big Bang's empirical successes and the bounce's theoretical elegance. We've journeyed through the physics, history, and evidence surrounding the Big Bang and Big Bounce theories. But stepping back from equations and observations, what does this debate really mean? How do these cosmic origin stories affect our understanding of reality, time, existence, and ourselves? First, consider what it means for time itself. If the Big Bang is correct with a true beginning, then time is finite into the past. There's a first moment, roughly 13.8 billion years ago, before which time didn't exist. This is mind-bending because our intuition treats time as a continuum stretching back without limit. Time itself is part of the universe, created along with space and matter. This finite time view has interesting implications. It means the universe has a definite age, a specific history with a starting point. Events can be ordered temporally from that beginning to now. This framework fits naturally with narrative thinking, telling the story of cosmic evolution. Alternatively, if the bounce is correct, time might extend much further back than we typically imagine, or have no starting point at all. The universe oscillates through transformations, but time itself has no beginning. This challenges our intuition differently. How do we make sense of time stretching back without limit? Some models finesse this by proposing that while transformations extend back without limit, information from distant past phases is lost. Each rebound scrambles conditions so thoroughly that traces of earlier phases vanish. The effective beginning of observable history is the most recent rebound, even though reality extends further back. These different time concepts connect to debates about whether time is fundamental or emergent. Some physicists argue time is a fundamental feature of reality. Others suggest time emerges from more fundamental timeless physics, much like temperature emerges from molecular motion. Let's think about multiverses, another implication of both theories. Perpetual inflation, often paired with the Big Bang, generates a multiverse of pocket universes with different properties. Our observable universe is one pocket where conditions allow life. This explains fine-tuning through anthropic selection. We exist in this universe because it allows our existence. Some rebounding models also imply a kind of multiverse across time. Each transformation might have different properties, different physical laws or constants. We observe this phase's properties because they allow observation. Previous and future phases might be radically different. The multiverse concept is controversial. Critics argue it's unfalsifiable, violating scientific methodology. If we can never observe other universes, how can we test multiverse theories? Proponents respond that multiverse theories make predictions within our universe that can be tested. Consider what these theories mean for life's existence. In a Big Bang universe, fine-tuned for life, perhaps through anthropic selection in a multiverse, our existence seems contingent. We happen to occupy a universe where conditions allow complexity. In a rebounding universe, life might arise repeatedly across transformations, or perhaps only in phases with appropriate conditions. This connects to questions about extraterrestrial life. If the universe is vast and old, with billions of galaxies each containing billions of stars, life should be common if it arises readily from chemistry. The Fermi paradox asks why we haven't detected obvious signs of advanced civilizations if they're common. In a rebounding universe, there's a possibility, purely speculative, of information transfer between phases. Could advanced civilizations encode information that survives the rebound? Could messages be sent to future transformations? These ideas are science fiction more than science, but they illustrate how cosmic origin stories inspire imagination. Let's talk about fate. If the Big Bang leads to perpetual expansion, the universe faces a cold, dark future. Stars will burn out, galaxies drift apart, black holes evaporate, and eventually nothing remains but dilute radiation in ever-expanding space. This big freeze scenario is desolate, but seems unavoidable in standard cosmology with dark energy. A rebounding universe offers a different fate. The expansion might reverse, leading to contraction and eventual rebound into a new phase. This is arguably more optimistic, suggesting cosmic renewal rather than permanent death. However, any structures or information from our phase would be destroyed or scrambled beyond recognition. Some physicists speculate about escaping cosmic doom. Could advanced civilizations manipulate spacetime to survive universal contraction or create new pocket universes? Could information be preserved through rebounding transitions? These ideas push into untested physics. There's a spiritual dimension to these questions that can't be ignored. Many religious traditions have creation stories explaining the universe's origin. How do scientific cosmology and religious belief interact? The Big Bang raises questions about first causes that some interpret as supporting belief in a creator. Others argue that quantum mechanics allows the universe to begin without external cause. These worldview connections reflect how the Big Bang versus bounce debate extends beyond pure physics into questions about meaning and purpose. The Judeo-Christian tradition speaks of creation from nothing, aligning with Big Bang thinking where everything has a definite starting point. Eastern traditions like Hinduism and Buddhism often describe recurring time, with the universe going through vast transformations called kalpas, resonating with bounce cosmology. Atheists and agnostics also engage with cosmology philosophically. The Big Bang raises questions about first causes. Rebounding cosmology sidesteps creation questions by having no beginning to explain. These debates probably won't be resolved by physics alone. Education is another consideration. How do we teach cosmology? The Big Bang is standard textbook material. Alternative models are mentioned, if at all, as speculative alternatives. This might change if observations favor these theories. Science education must balance teaching current best understanding while acknowledging open questions. There's risk in oversimplifying. Telling students the universe began with the Big Bang without explaining problems or alternatives does a disservice. Good science education conveys both what we know confidently and where mysteries remain. Public understanding affects support for research. Funding comes ultimately from society. When people appreciate the profound questions cosmology addresses and the methods used, they're more likely to support continued exploration. There's also pure wonder. Whether the universe began in a Big Bang or has been rebounding timelessly, both scenarios are staggering. We live in a cosmos spanning 93 billion light-years across, containing trillions of galaxies, evolving over billions of years. The fact that we, made of atoms forged in stars, can understand even fragments of this story is remarkable. This wonder motivates people into science careers. Children who learn about these theories might become the physicists solving these mysteries in coming decades. They'll have tools we don't, observations we can't make, and perhaps insights we haven't anticipated. Looking forward, the next few decades will likely bring major developments. James Webb observations will continue through the 20s. Gravitational wave astronomy will mature, with LISA launching and detecting primordial signals. New cosmic microwave background experiments will push polarization measurements further. Euclid and Roman telescopes will map cosmic structure with unprecedented detail. These missions might answer the Big Bang versus bounce question, or they might reveal that the truth is more complex. New theories combining elements of both, or introducing completely novel concepts, could emerge. The history of science is full of surprises. Quantum gravity remains the key frontier. Until we have a complete theory merging quantum mechanics with general relativity, our understanding of extreme conditions will remain incomplete. Progress in string theory, loop quantum gravity, or other approaches might provide breakthroughs. Artificial intelligence and machine learning are also changing cosmology research. These tools can analyze massive datasets, finding patterns humans might miss. They can run sophisticated simulations exploring parameter spaces too large for traditional methods. Citizen science offers another opportunity. Projects like Galaxy Zoo have enlisted millions of volunteers to classify galaxies, contributing to genuine research. Future projects might involve searching for anomalies in cosmic microwave background maps. Philosophy of science will continue grappling with cosmology's unique challenges. Unlike laboratory experiments, we can't rerun the universe's history or test theories by creating new universes. What does this mean for verification and falsification? These epistemological questions need ongoing attention. Ultimately, this debate represents humanity's attempt to answer perhaps the most fundamental question possible. Where did everything come from? How did it begin? Or did it begin at all? These questions transcend science, touching philosophy, religion, and our deepest curiosities about existence. We're fortunate to live when these questions are moving from pure speculation to testable science. Our telescopes can see nearly to the observable universe's edge. Our equations can describe conditions moments after the universe's beginning or rebound. Previous generations could only imagine and philosophize. We can actually investigate. But let's maintain humility. The universe has surprised us repeatedly throughout scientific history. Dark matter, dark energy, cosmic acceleration. These discoveries overturned assumptions. Whatever we currently think about cosmic origins might be revised as observations continue. This uncertainty isn't weakness, it's science's strength. By remaining open to revision and following evidence wherever it leads, science corrects errors and converges toward truth. Cosmologists today hold their theories more tentatively than previous generations, recognizing how much remains unknown. So here we are, 13.8 billion years after the Big Bang, or an unknown time after the most recent rebound. Either way, we exist as organized patterns of atoms contemplating our cosmic origins. We've built theories grounded in physics and mathematics. We've launched telescopes to observe the universe's farthest reaches. We've gathered evidence pointing toward truths about reality's fundamental nature. The debate will continue until observations decisively favor one or point towards something new. Scientists will refine theories, make predictions, and test them. The process is messy and uncertain, but it's working. We understand far more now than a century ago. Whatever the ultimate answer, the question itself is worth pursuing. Understanding where we came from, how the universe works, and what might come next enriches human existence. It gives perspective on our place in nature. It reveals the universe's profound strangeness and beauty. The universe, whether it began with a bang or has been rebounding like a cosmic yo-yo through time without end, is an amazing place. The fact that a species of curious primates on one small planet has figured out so much about cosmic history is testament to intelligence, curiosity, and the scientific method's power. Keep looking up. Keep asking questions. Follow the discoveries coming from space telescopes and gravitational wave observatories. These aren't abstract academic pursuits. They're humanity's ongoing attempt to understand the reality we inhabit. Whether through a bang or a rebound, whether with a beginning or existing timelessly, the universe is here, and so are we, asking these incredible questions and slowly, painstakingly finding answers. That's a remarkable thing. The story is far from over. The next chapters will be written by observations yet to be made, by theories yet to be developed, by people who aren't even born yet but will carry the quest forward. The ultimate question remains open. Did our universe explode into existence from nothing, or has it been rebounding through cycles without end? We don't know for certain yet, but we're asking the right questions, building the right tools, and making progress. The search for understanding continues, and we're all part of it, witnessing one of the great intellectual adventures in human history. Thank you for joining this deep dive into cosmic origins. Keep wondering, keep questioning, and keep looking forward to the discoveries that will surely come. The universe has more surprises waiting for us, and figuring them out is what makes the journey worthwhile. Understanding the mathematics behind these theories adds another layer of appreciation. Einstein's field equations of general relativity look deceptively simple on paper, but they encode incredible complexity. The equations relate the curvature of spacetime to the distribution of matter and energy. Solving them for cosmological scenarios involves sophisticated mathematics and often requires numerical simulations on powerful computers. When Friedman solved Einstein's equations for a homogeneous isotropic universe in the 1920s, he found solutions describing expansion or contraction. These Friedman equations form the basis of modern cosmology. They connect the universe's expansion rate to its matter and energy density. Input the current expansion rate and densities, and the equations tell you the universe's age and future evolution. Loop quantum gravity approaches these equations differently. It quantizes geometry itself, replacing continuous space with discrete structures at the Planck scale. This discreteness prevents densities from becoming boundless, providing a natural mechanism for the rebound. The mathematics is challenging, involving sophisticated concepts from differential geometry and quantum theory, but it yields concrete predictions about the early universe that can be tested. String theory offers yet another mathematical framework. It proposes that fundamental particles aren't points, but tiny vibrating strings. Different vibration patterns correspond to different particles. String theory requires extra spatial dimensions beyond the 3 we experience, typically 6 or 7 additional dimensions curled up at subatomic scales. In string theory's ekpyrotic scenario, our universe is a 3-dimensional brane in higher dimensional space. Collisions between branes release energy appearing to us as the Big Bang. The mathematics describing branes and their interactions is complex, involving advanced concepts from algebraic topology and differential geometry. All these mathematical approaches share common features. They attempt to extend physics into regimes we can't directly observe, using mathematical consistency and theoretical principles as guides. They make predictions that future observations might test. They represent humanity's attempt to use mathematics and logic to understand nature beyond what we can directly perceive. The role of mathematics in physics deserves emphasis. Mathematics isn't just a tool for calculation. It's a language for precisely expressing physical ideas and relationships. When equations predict phenomena that experiments then confirm, it reveals deep connections between abstract mathematics and physical reality. Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences. This effectiveness gives confidence that even when extrapolating beyond observable ranges, mathematics can guide us toward truth. If equations work perfectly in regimes we can test, we have reason to trust them in regimes we can't yet test, at least until observations prove otherwise. This is why theoretical physicists take mathematical elegance and consistency seriously. Of course, mathematics alone isn't enough. Theories must be tested against observations. No matter how elegant or mathematically consistent, a theory that contradicts experiments must be revised or abandoned. This interplay between mathematical theory and empirical observation drives physics forward. The cosmic microwave background deserves deeper exploration beyond what we covered in Chapter 3. When Penzias and Wilson discovered it in 1965, they were initially just trying to understand noise in their antenna. The antenna was built for satellite communications, a large horn-shaped structure pointing at the sky. No matter where they pointed it, they detected excess noise at microwave frequencies. They checked everything. Was it interference from New York City? No, the signal was the same at all times. Was it atmospheric effects? No, the intensity didn't vary with weather or seasons. They even considered whether pigeon droppings inside the antenna might be the source. They cleaned out the droppings, catching the pigeons and relocating them. The birds returned and left more droppings. Finally, they realized this wasn't noise at all. It was a genuine signal from space, uniform in all directions, with a temperature of about 3 degrees Kelvin. At Bell Labs, only about 40 miles away, a team led by Robert Dick had been planning to build an antenna to search for exactly this signal. When Dick heard about Penzias and Wilson's finding, he reportedly told his team, "Boys, we've been scooped." The discovery was monumental. Here was direct evidence for the Big Bang, the leftover heat from the universe's hot beginning. The microwave background wasn't just detected in one direction or one measurement. It fills the entire sky uniformly, exactly as predicted. This discovery transformed cosmology from a data-poor field with lots of speculation into a precision science with actual measurements constraining theories. Before this discovery, scientists debated whether the Big Bang or steady-state theory was correct, with relatively limited evidence. After the discovery, the evidence overwhelmingly favored the Big Bang. Over following decades, experiments measured the cosmic microwave background with increasing precision. Satellites mapped its temperature variations across the sky. These tiny fluctuations encode enormous information. They show us the seeds of galaxies, slight overdensities where matter would eventually clump together under gravity. The physics of these fluctuations is beautiful. In the early universe before atoms formed, space was filled with hot plasma, a mixture of electrons and protons with photons constantly scattering off them. Pressure gradients in this plasma created sound waves, oscillations of density and temperature propagating at about 60% light speed. These acoustic oscillations left imprints we can still see today. Regions that were compressed appear slightly hotter. Regions that were rarefied appear slightly cooler. The sizes of these hot and cold patches depend on how far sound could travel in 380,000 years, giving us a standard ruler to measure cosmic distances and geometry. All this detail demonstrates the power of modern cosmology. We're not just speculating about the universe's origins. We have detailed observations constraining theories. Every measurement adds information, either supporting theories or forcing revisions. Looking toward the future, upcoming experiments will continue refining our understanding. The Vera Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time starting in the mid-2020s. This telescope will photograph the entire visible sky every few nights, creating an enormous dataset tracking how the universe changes over time. The Square Kilometre Array, a radio telescope network spanning South Africa and Australia, will eventually have collecting area of 1 square kilometre, far larger than any previous radio telescope. It will probe neutral hydrogen across cosmic time, mapping how gas evolved into stars and galaxies. Space missions continue pushing forward. The European Space Agency's Athena X-ray Observatory, planned for the 2030 launch, will study hot gas in galaxy clusters and map the universe's large-scale structure through X-ray emission. Together with the Roman telescope, These missions will provide unprecedented data about cosmic evolution. All of these experiments and observations serve a common purpose: understanding our universe's nature. Whether they ultimately support the Big Bang, the bounce, or some synthesis of both, they advance human knowledge. Each measurement constrains possibilities, ruling out theories that don't match observations and supporting those that do. The debate between cosmic origin theories also highlights how science handles uncertainty. Unlike dogmatic belief systems that claim absolute certainty, science acknowledges when it doesn't know. The honest admission that we're unsure whether the universe had a beginning or has existed perpetually is a feature, not a bug. This flexibility has led to major paradigm shifts throughout history. Copernicus moved Earth from the cosmic center. Darwin showed species evolve rather than being immutably created. Einstein revealed space and time as relative and intertwined. Quantum mechanics demonstrated reality is probabilistic at small scales. Each shift challenged prevailing assumptions and sometimes faced resistance before being accepted. Today's debate about cosmic origins follows this pattern. We have competing theories making different predictions. As observations improve, we'll gain clarity about which better describes reality. This might vindicate the Big Bang framework, favor the bounce, or reveal something unexpected requiring new theoretical development. The collaborative nature of science often goes unappreciated. Individual scientists get credit for discoveries, but progress really comes from communities working together, checking each other's work, building on previous results, and pushing knowledge forward incrementally. The Big Bang theory wasn't developed by one person, but by dozens of contributors over decades. Education and public outreach play crucial roles. When people understand what scientists are doing and why it matters, they support continued research. Funding for basic science comes ultimately from society, whether through government grants or private philanthropy. Explaining these profound questions and the methods used to address them helps people appreciate why cosmology deserves resources. Moreover, cosmology inspires. Learning about the universe's vastness and our cosmic origins can profoundly affect worldview. It provides perspective, showing how our everyday concerns fit into immense scales of space and time. It reveals our connection to the cosmos, how atoms in our bodies were forged in stellar furnaces billions of years ago. These inspirations drive people into science careers. Children who learn about the Big Bang or bounce might become the physicists solving these mysteries in coming decades. They'll have access to observations and tools we can only imagine. They'll likely discover things we haven't anticipated. That's the nature of science. The quest to understand cosmic origins represents one of humanity's greatest intellectual achievements. We've moved from mythological creation stories to mathematical theories tested against observations spanning billions of light years. We've developed technologies capable of detecting radiation from when the universe was 380,000 years old. We've used mathematics to describe conditions fractions of a second after the beginning or rebound. This progress happened through the collective efforts of thousands of scientists over more than a century. It required developing new mathematical frameworks, building ever more sensitive instruments, and maintaining intellectual humility in the face of cosmic mysteries. The journey isn't over. Each answer raises new questions. Each observation reveals new puzzles. The universe continues to surprise us. Just when we think we have reality figured out, new observations reveal unexpected phenomena. Dark matter was discovered through its gravitational effects on galaxies. Dark energy was found through measurements of distant supernovae showing accelerating expansion. The cosmic microwave background revealed the universe's baby picture. Gravitational waves opened an entirely new window on the cosmos. Future surprises surely await. The James Webb Space Telescope has already revealed galaxies that challenge our understanding of early cosmic history. Future missions will undoubtedly uncover more unexpected phenomena. Each discovery enriches our understanding, while often raising new questions. The interplay between theory and observation drives progress. Theorists propose ideas and make predictions. Observers design experiments and collect data. When observations match predictions, theories gain support. When observations contradict predictions, theories must be revised or abandoned. This feedback loop gradually refines our understanding. Sometimes, observations precede theory. Dark matter and dark energy were discovered observationally before theoretical frameworks explained them. We still don't have complete theories for these phenomena. Other times, theory predicts phenomena before observations confirm them. Einstein predicted gravitational waves in 1916, but they weren't directly detected until 2015, nearly a century later. The Big Bang versus bounce debate exemplifies this process. Both frameworks are mathematically consistent and physically motivated. Both make predictions. As observations accumulate, we'll determine which better matches reality. This might take decades, but the scientific method works. Eventually, nature reveals her secrets. Meanwhile, these theories inspire and challenge us. They push the boundaries of human knowledge into the deepest questions about existence. Whether the universe began or has always existed, whether time itself had a starting point, these questions touch on profound mysteries that humans have wondered about since developing self-awareness. We're privileged to live when these questions transition from pure philosophy into testable science. We can actually investigate the universe's origins through observations and experiments, rather than just philosophical speculation. This represents an extraordinary moment in human intellectual history. The journey of discovery continues. Each observation adds knowledge. Each theoretical development offers new perspectives. The debate over cosmic origins remains open, inviting investigation and debate. Scientists around the world work on these problems, using different approaches and expertise. So while we don't yet know definitively whether our universe began with a bang or has been rebounding through time without end, we're making progress. Observations continually improve. Theories become more sophisticated. The debate sharpens. Eventually, nature will reveal which framework better describes reality. Until then, we appreciate both the Big Bang's empirical successes and the bounce's theoretical elegance, recognizing that truth might be more subtle than either picture alone suggests. The quest continues, and we're all part of it, asking questions and seeking answers about our cosmic origins. This is what makes science so exciting and important. We're not just solving puzzles, we're uncovering fundamental truths about reality itself. The history of how we arrived at these competing theories reveals important lessons about how science works. Scientific progress isn't a straight line from ignorance to knowledge. It's a winding path, with false starts, competing ideas, brilliant insights, lucky accidents, and gradual refinement through evidence. Consider how dramatically our view of the universe has changed over just the past century. In 1920, most astronomers thought the Milky Way was the entire universe. Edwin Hubble's discovery that spiral nebulae were actually distant galaxies expanded the known cosmos by orders of magnitude. Before Hubble, the universe seemed static and eternal. After his observations of cosmic expansion, we realized the universe has a history, a direction, possibly a beginning. This transformation happened through careful observations not just theoretical speculation. Hubble didn't sit in an office and decide the universe should expand. He went to Mount Wilson Observatory night after night, photographed galaxies, measured Cepheid variables, calculated distances, and compared them to redshifts. The data led him to an unavoidable conclusion that contradicted prevailing assumptions. This pattern repeats throughout cosmology's history. Predictions are made, observations are conducted, and reality surprises us. Sometimes, observations confirm predictions, as with the cosmic microwave background. Other times, they force revisions, as with the discovery of accelerating expansion in 1998. Scientists expected the universe's expansion to be slowing down due to gravity. Instead, supernovae observations showed it was speeding up, requiring the introduction of dark energy into cosmological models. Dark energy exemplifies how much we still don't understand. It comprises about 68% of the universe's total mass energy content, yet we don't know what it is. The leading candidate is vacuum energy, the energy inherent to empty space itself. But calculations of vacuum energy from quantum field theory give results about 120 orders of magnitude too large. That's 1, followed by 120 zeros, an absurd discrepancy. This enormous mismatch between theory and observation is sometimes called the worst prediction in the history of physics. Yet somehow, dark energy exists at just the right level to cause accelerating expansion without tearing the universe apart. Why? We don't know. This remains one of the deepest mysteries in physics. Dark matter presents similar puzzles. We know it exists because we observe its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters contain more gravitating mass than we can account for with stars and gas. Gravitational lensing, where massive objects bend light, reveals the presence of unseen mass. Multiple independent lines of evidence all point to the same conclusion. There's about 5 times more dark matter than ordinary matter in the universe. But we don't know what dark matter is made of. Leading candidates include weakly interacting massive particles, or WIMPs, and axions, hypothetical particles predicted by some theories. Despite decades of searches with increasingly sensitive detectors, we haven't directly detected dark matter particles yet. These mysteries don't invalidate the Big Bang theory. They show that while we understand the universe's overall evolution, we don't understand most of what composes it. This is actually exciting rather than discouraging. It means there are major discoveries still to be made, fundamental questions still to be answered. The development of inflation theory demonstrates how theoretical work addresses observational puzzles. In the late 1970s, cosmologists recognized problems with the standard Big Bang model. The horizon problem and flatness problem seem to require fine-tuned initial conditions. Why should the universe start in such a special state? Alan Guth, working at Cornell and Stanford in the late 1970s and early 1980s, realized that a brief period of exponential expansion could solve these problems naturally. If the universe underwent rapid inflation very early on, it would explain both the uniformity we observe and the flatness of space. Guth published his idea in 1981, and it quickly gained attention. But Guth's original inflation model had problems. It couldn't end inflation gracefully. The universe would expand forever, never transitioning to the normal expansion we observe. Other physicists, including André Linde, Andreas Albrecht, and Paul Steinhardt, developed improved inflation models that solved this problem. By the mid-1980s, inflation had become the leading explanation for the universe's initial conditions. Inflation makes specific predictions that can be tested. It predicts the universe should be spatially flat, which observations confirm. It predicts nearly scale invariant density fluctuations, which cosmic microwave background observations confirm. It predicts primordial gravitational waves at levels that might be detectable by future experiments. Each confirmation increases confidence in the theory. However, inflation also has features some physicists find troubling. It predicts perpetual inflation in most models, where inflation never completely stops but continues in some regions of space forever. This produces a multiverse of pocket universes with different properties. Our observable universe is just one pocket among potentially limitless others. The multiverse concept raises philosophical and scientific questions. If we can never observe other universes, can the multiverse hypothesis be considered scientific? Some argue it's unfalsifiable and therefore not science. Others counter that multiverse theories make predictions within our observable universe that can be tested, making them scientific even if we can't directly observe other universes. This debate touches on deep questions about what makes something scientific. Karl Popper argued that falsifiability is the key criterion. A theory must make predictions that could potentially be proven wrong. Thomas Kuhn emphasized paradigm shifts and the social nature of scientific revolutions. More recent philosophers of science have argued for more nuanced views, recognizing that scientific theories are often tested holistically rather than individually. Cosmology presents unique challenges for traditional scientific methodology. We can't do controlled experiments on the universe. We can't rerun cosmic history with different initial conditions to see what happens. We observe a single universe from a single vantage point at a single time. How do we do science under these constraints? Cosmologists deal with this through multiple strategies. They look for natural experiments, situations where the universe itself provides different conditions to compare. They use statistical methods to extract maximum information from available data. They develop mathematical models that can be simulated on computers, allowing exploration of different scenarios. They seek multiple independent lines of evidence that converge on the same conclusions. The cosmic microwave background exemplifies this approach. Multiple satellites with different instruments and analysis methods have measured it. Ground-based and balloon-borne experiments provide complementary data. Different teams analyze the data independently. All reach consistent conclusions about the universe's age, composition, and geometry. This convergence of evidence from multiple sources provides strong support for the underlying theory. Gravitational wave astronomy, still in its infancy, promises to open entirely new windows on the cosmos. When LIGO detected gravitational waves from merging black holes in 2015, it confirmed a prediction Einstein made 99 years earlier. It also demonstrated that we can observe the universe through ripples in space-time itself, not just electromagnetic radiation. Future gravitational wave detectors will probe lower frequencies, accessing signals from the early universe. If the Big Bang or a quantum rebound produced gravitational waves, these primordial signals might still be propagating through space-time. Detecting them would provide direct evidence about conditions in the universe's first moments, potentially distinguishing between different theories of cosmic origins. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will detect gravitational waves with wavelengths too long to observe from Earth. It will consist of 3 spacecraft flying in formation, separated by millions of miles, forming a giant gravitational wave detector in space. LISA will search for signals from supermassive black hole mergers, exotic compact objects, and potentially primordial sources from the early universe. Even more ambitious concepts are being discussed for future decades. A third-generation ground-based gravitational wave detector called Cosmic Explorer might have arms 25 miles long, 10 times longer than LIGO. The Einstein telescope, proposed for construction in Europe, would be a triangular underground facility with 10-kilometer arms. These detectors would be so sensitive they could detect gravitational waves from the most distant reaches of the observable universe. Each new observational capability reveals previously hidden aspects of the cosmos. Radio astronomy, developed in the 1930s and 40s, showed us violent processes invisible to optical telescopes. X-ray astronomy, made possible by satellites above Earth's atmosphere, revealed hot gas in galaxy clusters and energetic phenomena around black holes. Infrared astronomy penetrates dust clouds to observe star formation and distant galaxies. Gamma-ray astronomy detects the most energetic events in the universe. The James Webb Space Telescope combines large mirror size with infrared capabilities, allowing it to see the earliest galaxies forming in the universe's first few 100 million years. Its observations are already challenging our understanding of how quickly galaxies assembled after the Big Bang or rebound. Some galaxies appear so massive and well-developed at such early times that they're difficult to explain with standard models. These challenges don't mean the Big Bang theory is wrong. More likely, they indicate our models of galaxy formation need refinement. Perhaps early star formation was more efficient than we thought. Maybe feedback processes from supernovae and black holes worked differently in the early universe. Or possibly dark matter clumped faster than simulations predict, allowing galaxies to form earlier. Resolving these puzzles will require combining JWST observations with theoretical work and improved simulations. It will take time, more data, and careful analysis. This is how science progresses, through iterative refinement driven by observations that challenge our understanding. The interplay between observation and theory is never simple or straightforward. Observations don't come with labels saying, "This supports theory A," or "This disproves theory B." Data must be analyzed, systematic errors identified and corrected, statistical significance calculated. Theoretical predictions must be refined to account for complicating factors. The process involves judgment calls, assumptions, and interpretation. This is why scientific conclusions are always tentative, subject to revision based on new evidence. We say theories are well supported or highly probable rather than proven. This isn't weakness or uncertainty in a problematic sense. It's intellectual honesty about the limits of human knowledge and the provisional nature of scientific understanding. The Big Bang theory is extraordinarily well supported by multiple independent lines of evidence. Cosmic expansion, the microwave background, light element abundances, and large-scale structure all point to a hot, dense, early state that evolved into the universe we observe today. This doesn't mean every detail is correct or that the theory is complete, but the overall framework is solid. The bounce theory, by contrast, is more speculative. It makes theoretical sense and addresses real problems in Big Bang cosmology, but it lacks the observational support that would elevate it from interesting possibility to well-established theory. This could change if future observations detect predicted signatures of a quantum rebound or previous phases. Until then, it remains an intriguing alternative worth developing and testing. Science works by holding multiple possibilities in mind simultaneously, favoring those with stronger evidence while remaining open to alternatives. This balance between confidence in well-supported theories and openness to revision is what makes science reliable. We trust scientific conclusions not because scientists claim certainty, but because conclusions are proportioned to evidence and subject to testing. The cosmic origin debate illustrates this beautifully. We have the Big Bang framework, strongly supported but with acknowledged problems. We have bounce alternatives that address those problems but need observational confirmation. We continue developing both frameworks, making predictions and conducting observations to test them. Eventually, evidence will favor one or point towards something we haven't imagined yet. This process takes patience. Science doesn't provide instant answers to profound questions. It makes steady progress through careful observation and rigorous thinking. The payoff is genuine understanding grounded in evidence rather than speculation or wishful thinking. Looking back over the past century, the progress is remarkable. We've gone from thinking the Milky Way was the entire universe to mapping billions of galaxies across billions of light years. We've determined the universe's age to within about 0.5%. We've measured its composition, geometry, and expansion rate. We've traced cosmic history from fractions of a second after the beginning or rebound to the present day. This achievement resulted from the collaborative efforts of thousands of scientists across multiple generations and many nations. It required developing new technologies, from better telescopes to more sensitive detectors to faster computers for simulations. It needed theoretical insights, connecting observations to underlying physics. It demanded careful attention to detail, checking and rechecking results, and intellectual honesty when observations contradicted expectations. The journey continues. Future generations will look back on our current understanding as we look back on the cosmology of a century ago, recognizing both genuine insights and limitations. They'll have access to observations we can't make and theoretical frameworks we haven't developed. They'll answer questions we can't yet answer and discover phenomena we haven't imagined. That's the beauty of science. It's never finished, never complete. Each answer raises new questions. Each observation reveals new mysteries. The universe continues to surprise us, rewarding our curiosity with deeper understanding while humbling us with the vastness of what remains unknown. Whether the universe began with a bang or has been bouncing through phases without end, the fact that we can ask this question and actually investigate it through observations is extraordinary. We're products of the universe studying itself, atoms arranged in patterns capable of contemplating cosmic origins. However the debate resolves, the journey of discovery is valuable in itself, expanding human knowledge and perspective. There's something deeply human about asking where everything came from. Children ask it. Philosophers ponder it. Scientists investigate it. Every culture throughout history has created stories to explain cosmic origins. What makes our current era special is that we can move beyond stories and myths to actual investigation through observation and experiment. This transition from mythology to science didn't diminish the wonder or profundity of these questions. If anything, real evidence makes them more awe-inspiring. Ancient creation myths are beautiful and psychologically meaningful, but they're human inventions. The Big Bang and Big Bounce theories, by contrast, are attempts to describe what actually happened, constrained by observations and mathematics. When we detect radiation from 380,000 years after the universe's beginning, We're not making up a story. We're seeing direct evidence from cosmic history. This evidence-based approach to understanding cosmic origins represents one of humanity's greatest intellectual achievements. We've developed methods for reliably learning about nature, methods that work precisely because they're not based on wishful thinking or cultural assumptions, but on careful observation and logical reasoning. The scientific method isn't perfect. Scientists make mistakes and have biases, but it's self-correcting. Wrong ideas eventually get weeded out through continued observation and testing. Consider what it means that we can measure the universe's age to within about 20 million years out of 13.8 billion. That's precision better than 1%. We can determine the universe's composition, knowing it's about 5% ordinary matter, 27% dark matter, and 68% dark energy. We can map the cosmic microwave background's temperature variations to parts per million. We can detect gravitational waves from black hole collisions billions of light years away. These capabilities didn't exist 50 years ago, let alone a century ago. They resulted from sustained investment in scientific research and technology development. Society-funded telescopes, satellites, detectors, and the salaries of scientists to operate them and analyze the data. This investment paid off in knowledge about our universe and our place in it. But cosmology isn't just about satisfying curiosity. It has practical benefits too. Technologies developed for astronomical observations often find applications elsewhere. Charge-coupled devices, or CCDs, invented for telescopes, now capture images in every smartphone camera. Computer algorithms for analyzing astronomical data are used in medical imaging. Global positioning systems, or GPS, rely on relativistic corrections predicted by Einstein's theories that cosmologists use to understand the universe. More broadly, cosmology exemplifies how basic scientific research advances civilization. We don't study cosmic origins because it will cure diseases or improve agriculture next year. We study it because understanding our universe is intrinsically valuable and because basic research often leads to unexpected applications decades later. The quantum mechanics, developed in the early 20th century to understand atoms, now underlies all modern electronics. Nobody in 1925 predicted computers or smartphones, yet they emerged from that basic research. The cosmic origin debate also connects to questions about meaning and purpose that resonate beyond science. If the universe had a definite beginning, does that imply it has a purpose or direction? If it's existed perpetually through endless transformations, does that change how we think about existence and meaning? Different people answer these questions differently based on their philosophical and religious views. Science can't answer ultimate why questions. It describes how things work, what physical laws govern nature, what happened in cosmic history, but it can't tell us if there's meaning or purpose behind it all. That's a limitation science acknowledges. Questions about meaning, purpose, and value lie outside scientific methodology. They're important questions, just not ones science can address. This recognition helps clarify the relationship between science and religion. They address different kinds of questions. Science asks how the universe works and what happened. Religion asks why we're here and how we should live. These questions can be complementary rather than contradictory. Many scientists are religious, finding no conflict between their scientific work and their faith. Others are atheists or agnostics who find meaning in naturalistic frameworks. The key is recognizing what each domain can and can't address. Science can't prove or disprove the existence of God or answer questions about ultimate meaning. Religion can't determine the universe's age or composition or whether it began or has always existed. When each stays within its proper domain, they don't conflict. Conflicts arise when religious authorities make claims about the natural world that contradict evidence, or when scientists claim their work proves or disproves religious beliefs. The cosmic origin theories we've explored can be interpreted through various worldview lenses. Some religious people see the Big Bang as scientific confirmation of creation ex nihilo, from nothing. The universe having a beginning aligns with creation theology. Others see the bounce as compatible with religious concepts of cycles and recurrence. The universe transforming through endless phases resonates with some Eastern religious traditions. Secular humanists might view either theory as showing the universe doesn't require supernatural explanation. Natural processes governed by physical laws can account for cosmic evolution without invoking divine intervention. Or they might appreciate the mystery and wonder of existence, regardless of whether the universe began or has always existed. These different interpretations show that scientific theories don't dictate metaphysical or religious conclusions. The same evidence can be viewed through different philosophical frameworks. What matters is that we distinguish factual claims that science can investigate from value claims and meaning questions that require different approaches. Education in cosmology should reflect this complexity. Students should learn the scientific evidence and theories, understanding what we know and how we know it. But they should also appreciate the limits of scientific knowledge and the legitimate role of philosophical and religious perspectives on questions science can't address. This doesn't mean teaching religious creation stories as science. That's inappropriate. But it does mean acknowledging that science and religion address different kinds of questions and that thoughtful people can hold various views on ultimate meaning while accepting the same scientific evidence. The process of scientific discovery itself carries lessons applicable beyond science. Science teaches intellectual humility, recognizing that our current understanding is incomplete and subject to revision. It teaches respect for evidence and logical reasoning. It demonstrates the value of collaborative effort, as complex problems are solved through many people working together over long periods. It shows that disagreement and debate are healthy when grounded in evidence and conducted respectfully. These lessons are valuable for addressing all sorts of problems, not just scientific ones. Policy debates, ethical questions, and personal decisions all benefit from evidence-based thinking, intellectual humility, and respect for different perspectives. Science can't solve these problems directly. They involve values and priorities beyond scientific investigation. But scientific thinking provides useful tools. The cosmic origin debate also reminds us of our cosmic context. We're inhabitants of a planet orbiting an ordinary star in a galaxy containing hundreds of billions of stars, which is one of hundreds of billions of galaxies in the observable universe. Our entire existence occupies a tiny fraction of cosmic space and time. Earth formed about 4.5 billion years ago, less than a third of the universe's age. Complex life appeared relatively recently. Human civilization emerged in just the last few thousand years, a blink in cosmic time. This perspective is simultaneously humbling and inspiring. Humbling because it shows how small and temporary we are in the grand scheme of things. Inspiring because despite our tiny place in the cosmos, we can understand so much about it. We're made of atoms forged in stellar cores, assembled through billions of years of cosmic evolution, now capable of comprehending that very process. The universe has become conscious of itself through us. Whether the universe began with a bang or has been bouncing through phases without end, our existence is remarkable. The fact that the universe's laws and initial conditions allowed matter to organize into stars, planets, and eventually life and intelligence is extraordinary. Whether this is pure chance, anthropic selection in a multiverse, or evidence of purpose depends on interpretive frameworks beyond science. But the facts themselves are awe-inspiring regardless of interpretation. Looking to the future, cosmology will continue advancing through new observations and theoretical developments. Within the next few decades, we'll likely answer many current questions while discovering new ones. We might determine whether the universe began or has bounced through phases. We might discover what dark matter and dark energy are. We might detect primordial gravitational waves, revealing conditions in the universe's first moments. Or we might find something completely unexpected that requires rethinking our entire framework. Whatever happens, the journey of discovery will continue. Future generations will look back on our current understanding, appreciating our genuine insights while recognizing our limitations. They'll have capabilities we can't imagine, just as we have capabilities that scientists a century ago couldn't imagine. But they'll face the same fundamental challenge, trying to understand the universe through observation, reasoning, and evidence while acknowledging the limits of human knowledge. The cosmic origin question remains one of the most profound we can ask. Where did everything come from? How did it begin? Or did it begin at all? These questions touch on the deepest aspects of existence and reality. The fact that we can investigate them scientifically, making observations and testing theories, is a testament to human ingenuity and the power of the scientific method. Whether you favor the Big Bang, the bounce, or remain agnostic between them, the important thing is appreciating the questions and understanding the evidence. Science doesn't provide absolute certainty, but it offers the best method we have for understanding nature. By carefully observing the universe and rigorously testing theories against evidence, we gradually converge toward truth. The debate between Big Bang and bounce will continue until observations decisively favor one or reveal something new. Until then, we marvel at what we've learned, recognize what remains unknown, and continue the quest for understanding. This is the essence of science. Asking profound questions, gathering evidence, testing ideas, and always remaining open to revision based on new discoveries. That's what makes this such an exciting time to be alive. We're living through a golden age of cosmology, when ancient philosophical questions are becoming empirically testable. The next few decades will almost certainly bring major discoveries that reshape our understanding. Whatever those discoveries reveal, they'll deepen our comprehension of the universe and our place in it. The journey continues, and we're privileged to be part of it.